See, in our previous videos, many examples we have solved of double integration as well as triple integration also. See, now we are going to discuss some theory part. Okay, so today we are going to discuss this concept double integration. What is the actual meaning of it? Problems we have solved. So let us learn the theory behind it. Okay. So if you are familiar with Riemann integration, I can say it's simply an extension of Riemann integration. The concept is similar to Riemann integration. In the Riemann integration, what we do? We find area under the curve. But in double integration, we find volume under the surface. That means suppose we have a surface like this, whatever the volume below the surface, okay, that means surface as well as xy plane. Okay, so that volume we are going to find here. So let us learn what is that concept actually. So now first of all I will consider, so let I am considering let S is equal to AB cross CD. One rectangle I have considered. Okay, I will show you simultaneously what I am doing. In xy plane we will have like this. Suppose this is x, this is y. So here AB and here we have a CD. Okay. So AB cross CD, that means we will have this rectangle. Okay. And the same diagram, okay, the same rectangle in 3D, it will look like this. It will, so this is x axis, this one is y axis and this one is z axis. So this is AB cross CD. Okay, same rectangle I have drawn in 3D. Okay, after that what we do, I take a partition of closed interval AB. So see, let P1 is equal to partition. Okay, I will write in short. So see, P is equal to A is equal to x naught, x1 and so on, xn is equal to B. So see, here I am taking partition. X naught means A, x1 means one point here, x2 and so on. The last point xn is nothing but B. So if you take a partition of closed interval AB, it will introduce, okay, it will introduce the partition of this rectangle. Because of x1, I can draw a line here. Because of this x2, I can draw a line here, and similarly, okay, for remaining partitions also, we get a lines here. So that means this rectangle is divided now into small sub rectangles, right? So similarly, I will take P2 be the partition of this closed interval CD. So C is equal to y naught, y1 and so on. Ym is equal to D. So here I am taking a partition. Y naught means C1. After that y1, y2, y3, y4 and the last ym is equal to D. So because of this partition, we can draw lines here. Getting the point? So that means, so now this rectangle is subdivided into m into n subrectangles, right? So I can draw the partition like this. Getting? So here we have a partition, and because of these partitions we have got a region like this. Actually we have a function, one function here. Okay, I am drawing a function. So this is our f of xy. So this is a function we have. Getting? So it's just like a piece of cloth. If you see, you can consider. So actually it is over this rectangle. We have this one. Getting? So yeah, actually we have a rectangle R, okay, or you can say S. Because of this partition, it is divided into sub rectangles, and I can write each sub rectangle will be like this. Rij is equal to xi minus 1 xi into yj minus 1 yj. Okay, so that means each sub rectangle. So that means this is r11, r12, r13, r14, r21, r22, r23, r24. In this way I have denoted it by this one. Okay, after that, actually what will happen because of this partition, can you imagine, we have a surface like this, we have a base having a base as a rectangle, and it has a volume which is bounded by that surface and this base, and because of this partition, that total volume is divided into m into n pillars. You are getting? For each sub rectangle we will have pillars like this. Okay, so what will happen, now I am going to consider let capital Mij. Capital Mij, that is supremum of f of xy where xy belongs to Rij. That means for each Rij, for each subrectangle, the function will have maximum value. Somewhere it will have maximum value, right? So that maximum value will be capital Mij. For example, suppose you have a subrectangle like this, okay, and suppose there is one surface like this, and part of surface is like this. So function has a maximum value somewhere, that is small Mij. Similarly, the function will have minimum value somewhere, that is my small Mij. I'm talking about over this subrectangle. Getting? So see, I can write here our small Mij is equal to infimum of, that means minimum value, of f of xy, x comma y belongs to Rij. After that, I'm going to define UPF, or you can say upper sum. So here it is similar to the Riemann integration which I already studied in second year BSc. So UPF is equal to summation capital Mij into Arij. So maybe you will think that why I'm taking double summation, since we have two variables I and j, one summation for I and second summation for j, I running from 1 to m, j running from 1 to m. So what is actual meaning of it? A means area of Rij. So that means whatever the subrectangle we have, okay, so I'm calculating its area and I'm multiplying by Mij. Mij means height. That means area of base into height. This is nothing but volume. Getting? So that means we are actually calculating the volume of one pillar, okay, since I'm considering simply Rij. Similarly, LPF also I can define with the help of this small Mij. So same thing we have summation small Mij area of Rij. Okay, that means over a same subrectangle, I am calculating the maximum height of pillar and I am calculating the minimum height of pillar. We are doing the same. We are considering the same pillar. Getting? So see, pillar's upper surface of pillar will be like this, okay, it's bent, it's not plain. Then somewhere it will have maximum value, somewhere it will have minimum value. So the maximum value if you consider, you will have UPF, and the minimum value if you consider, you will have LPF. Okay. See, but the fact is, if you change the partition, value of UPF and LPF can be different. Getting? If anyone consider just 4 partitions, then value will be different. If you increase the partition 8, 16 like that, you will have a more partition. Okay, different values. Getting? So see, what we do, whatever the different values, I remove this diagram. I think all of you understood the meaning of it. Just a minute, I will remove. So for different partitions, we are having a different values of UPF and LPF. Okay, UPF, upper sum, I will take the least value of UPF. So we'll denote it by UF. UF, this is equal to infimum of UPF, where P is a partition, okay, simply P is partition, and LF is equal to supremum of LPF, okay, where again P is a partition of this S. See, whatever UPF means upper sum, I'm taking the infimum of upper sum, and lower sum, I'm taking a supremum of lower sum. You are getting my point? Upper sum, obviously it is greater than lower sum, but whatever the upper sum we have, I'm taking its infimum, and whatever the lower sum we have, we are taking its supremum. So I hope somewhere they will match. Okay, so if they will match, that means if UPF is equal to LPF, if it will happen that UF is equal to LF, if it will happen, then we can say the function is double integrable. Getting? And this is nothing but the actual value of double integration. If both of them are different, then function is not double integrable. Okay, so this is a simple concept we have. So if both of them are same, function is integrable. Both of them are different, function is not integrable. Okay, so this is the actual theory behind it, double integration. If you are already familiar with Riemann integration, then you can easily understand. Otherwise, revise the video and watch it again. Okay, make a screenshot of it if you want. Otherwise, we will stop. Thank you. Bye bye.